Okay, this week we begin to move into moisture, or water vapor, water. It really is a driving engine for a lot of the atmosphere and what you talk about as weather. All of us want to know, how humid is it outside? Is it going to rain today or not? Are we going to have a cloudy afternoon? Those are all things that we talk about and are interested in probably, and it may impact your activities. Maybe you were going for a run in the afternoon and wound up having a downpour of rain on top of you. It may feel good. Maybe you were just wanting to go for a picnic. And instead, there was this cloudy skies and it got cool. So all of that, think about it, comes from looking at the amount of moisture in the atmosphere. So see if we can come up with some stuff here. So first, we got to understand the cycling of water in the earth. What does that mean? Well, they want to show an example here of atmospheric rivers. You can see coming into California here an area, continuous clouds coming out of the southwestern Pacific, stretching across it and into California. Literally, that is an atmospheric river where there's a ton of moisture in that cloud band moving across and all the way into California, the northern part of California there. That happens sometimes in the wintertime when they get tremendous rainfalls in California because there may be low after low moving along those atmospheric rivers. However, there are other times when they don't form, and that leads to drought like we're seeing right now out there. And you can see the water vapor comes in initially at the low levels along the coast, dumping rain. Then it gradually rises, gets pushed up by the mountains, dumping even more snow and rain. So total amount of water is actually pretty small. You think about it, if all the water all over the world that was in the atmosphere fell out, basically it would equal about a depth of 1 inch. However, water is continually entering the atmosphere and leaving the atmosphere. Now, that's what this whole cycle of global water cycle is. So in it, oceans have evaporation. Oh yeah, there's also condensation, precipitation forming and falling back into the water. Over mountains, sometimes there's rainfall, even over land. And maybe there's runoff down a steep slope. If you lived in parts of West Virginia where there's into the valleys, I can tell you for a fact that the rain really runs down those slopes and drops into the valley very quickly, causing the rivers to rise very fast when that happens. So there's also times where the ground is very flat. Water sits there, takes a while to percolate into the ground, and even some of it does run off with time. So there are all different facts with how the water is handled. Trees. There's actually an area that they've studied in Oklahoma where they have a winter wheat crop. Winter wheat has great evapotranspiration, or transpiration of water vapor into the air from the leaves. It soaks it up from the ground. Well, during the time that crop's there, dew points, which are a measure of water vapor, are running in the 60s across that area. Once they cut it in early July, the dew points literally fall back into the 40s and 50s. That winter wheat makes a huge difference on the amount of moisture in the air in that part of Oklahoma. And these are just some of the phase changes of water. We've talked about them before. We understand a little bit about them now. Humidity, just a measure of water vapor, how much water vapor is in the air. We use different things to measure humidity. Vapor pressure. Water vapor has pressure. It's an atmospheric gas, so there's an amount of pressure to it. So that's one way of measuring it. If you know the vapor pressure, you can actually figure out how much water vapor out of that volume of air there is. Mixing ratio is another one, specific humidity. So let's look at some of these. If you looked at the vapor pressure over the whole world, the most amount of water vapor anywhere in the tropics, probably where it's very humid, maybe over the Amazon, is 4% of the atmosphere's mass in the lowest kilometer. That's it. That's not actually a large number. Mixing ratio is just the mass of water vapor per the mass of the remaining dry air. So think about it. Water vapor is less than 4%. It's not really making up a whole lot of that. So it's just a mass per mass. And specific humidity just adds the amount of water vapor into that other column, other side. Instead of just dry air, it now contains water vapor as well. So you get the total amount of air for the total amount of water vapor. They're not very far apart. Generally, they're going to be equal or very, very close to it. So say your air was completely saturated. Couldn't hold any more water. The mass of water vapor per unit volume of humid air is absolute humidity, or grams of water vapor per cubic meter of air. In other words, that amount of water vapor is the most that cubic meter of air can hold. So air at its maximum humidity is saturation. What does that mean? Well, think about it. Water is condensing and evaporating at an equal rate. In other words, the air can't add any more water, but at the same token, the clouds are forming and they're condensing. So there's a little bit of more water vapor condensing and a little bit of water vapor up to the clouds going back to water vapor. Right at that point is where we call saturation. So all those terms you just learned, vapor pressure, mixing ratio, etc., we just put saturation in front of them to name when they're totally saturated. In other words, the relative humidity at that point is really 100%. Heating water increases its kinetic energy. The water molecules start moving faster. They can more easily escape that water surface. So that is why the hotter the air, the more water vapor the air can hold before it becomes saturated, because of that kinetic energy increase. So here you can see it as the water vapor will increase with the temperature. The temperature actually is 140 degrees. It can hold 76.78 millibars to make it saturated. That's a heck of a lot of water. Yesterday, I had Elsa go by my house. I had temperatures in the mid-70s. And we had areas around me had over 5 inches of rain. There it is, 31.67 millibars. However, if that same kind of system had gone by in the wintertime, look at this, it's all the way down to 6. And oh yeah, over ice. Remember, ice is a solid, so even if you kind of warm it a little bit, it actually has a lower vapor pressure for saturation than liquid does. And it gets more so the colder the ice and the air get. Something that you're going to find pretty important later on to know. So relative humidity is just vapor pressure over saturation vapor pressure. So if I told you I had 35 millibars of vapor pressure and the saturation vapor pressure was 36 millibars, I would just divide those together and multiply it by 100 to get the relative humidity. So when somebody tells you the relative humidity is 98% outside, that's literally what they're telling you. The vapor pressure per saturation, or mixing ratio per saturation mixing ratio. One of the interesting things about vapor pressure, remember we just said that as temperatures increase, air can hold more moisture. So during the daytime, when the temperatures get colder, or get warmer, the amount of relative humidity typically goes down. Relative humidity will peak at the coldest time of day, typically around sunrise. That's why you have fog forming at that time, because that's when relative humidity may reach your 100% at that point in time. And then after the sun begins to come up, breaks up the fog, temperatures begin to rise, and the fog dissipates. Dew point is just another measure of moisture. It's something meteorologists use a lot. The temperature the air must cool to at some constant pressure to reach saturation. So when you see a dew point on a weather map, say the temperature is 75, the dew point is 65. That 5-degree separation is the difference between the air being saturated and not saturated. So what I am looking for a lot of times is, if it's raining into that air, I will bet you that either the dew point is going to rise or the temperature is going to cool. Remember, rain falling, evaporation taking place, so there's a cooling process. And they're going to try to meet somewhere in the middle. So a lot of times when you're looking at temperature and dew point, you can literally see how they're going to change depending on precipitation. One of the things, too, after a cold front goes through, cold air gets very dry when it's coming out of Canada. Remember, it has no source of moisture up there. So the dew point can be really, really low. And here you can see in the wintertime, dew points average well under freezing. Down in the 20s, most areas. Look at Ohio. Out in the summertime, air is warmer, 60s, well up into the 60s for dew points, even into the 70s, a lot of Florida and stuff. And more at my house, I'm by the ocean. So with this, condensation literally forms clouds. So as humidity increases when the air is cooled, we know that when air rises, it cools. We've talked about that over and over. So as the air parcel is rising, if you don't change the amount of moisture in that air parcel, at some point it's going to reach saturation. And when it reaches saturation, condensation is going to occur. Some of that moisture that was in the water vapor is going to transition into actual water droplets. And that's where the cloud forms. And as the air tends to cool further up, the higher it gets, more of that water vapor is going to transition into the cloud droplets. So if you started an air parcel that was 100% saturated and rose it up in the atmosphere, yes, the relative humidity is going to stay 100%. But the amount of water vapor in that air parcel is going to decrease because it's going to transition into water droplets. And you will see a question like that this week. So now we're going to talk a little bit about stability. If an air parcel is heavier, how the heck's an air parcel going to be heavier than around air? Well, parcel stability is based on density. So if an air parcel is colder than the surrounding air, there's more mass to it, its density is higher, it's going to tend to sink. If, on the other hand, there's less mass to it, density is a little less than the surrounding air, it's going to tend to rise. If you cool an air parcel that's dry up the way through up the atmosphere, it's going to cool at a steady rate, basically 9.8 degrees Celsius for 1,000 meters. However, if you mix moisture into that curve, remember as the air parcel continues to cool and becomes saturated, moisture is going to begin the condensation process. Condensation releases heat so that our surrounding air is being warmed as the air parcel begins to become a cloud. So actually the air parcel becomes warmer and warmer. So instead of being 9.8 degrees Celsius when the air is saturated, it's actually around 6. So the air parcel is not necessarily going to be as stable in moist air. The idea is to know whether look at the temperatures of that air parcel and compare it to the actual temperature of the surrounding air. If the air parcel's temperature is colder, then it's going to tend to want to sink. It's stable. If the air parcel's temperature is warmer, it's going to tend to want to rise. So what happens in a cloud? When the air parcel in the cloud gets condensation going on, it begins to warm because of the condensation. What happens is the surrounding air around it is still cooling at the same rate probably, but that air parcel is no longer cooling at that rate. It's cooling about 2 or 3 degrees less per 1,000 meters. And if that happens, that means it's going to be warmer as it's going up. So a lot of times, moist air is going to be unstable versus dry air. And here you can see the conditional instability and absolute instability. And this is what causes an air parcel to begin to rise. Might be convection from the Earth. And then if it becomes unstable, it begins to rise even more. Sun's heating can do it. A front, warm front, cold front, both of them will lift an air parcel. And once you get that air lifting, maybe it will become stable, maybe it won't. Mountains will lift them. And then there are rain shadows where the air comes down the other side of the mountain. If it's going down, it's warming, or it's drying. Convergence of wind, like sea breezes that occur over Florida. So with that, let's take a quick peek here at just a couple things. Here is a water vapor image right now. Moisture coming up from the south into South Florida. Moisture coming up from the Gulf of Mexico all the way up just off the East Coast and getting wrapped into Elsa up here. So Elsa's moisture is actually coming off the Caribbean Ocean all the way up and into that area. More moisture is coming up out of the Gulf of Mexico here, and this is along a line of cold front here, generating some precipitation. And you can see here very dry air coming out of the desert southwest, moving in, causing drying in this area. So water vapor imagery is a very, very powerful tool. You can really see where the water vapor is, where it's dry aloft. This isn't looking at the surface. But one of the things looking at the surface, though, you can look at the surface and see dew points. They're on the lower left-hand side of a station plot. 72-degree dew point, 73-degree dew point. Look up here, 57-degree dew point. In the drier, colder air, 59-degree dew point. Over here along Elsa, 75, 78-degree dew point coming up. 61, 58-degree dew point up by Lake Erie today. So major changes as far as dew points across the country. Oh yeah, look out in the southwest. Winds are coming down off the mountains. Dew points in the 40s out in California. Finally, I just wanted to talk about stability. Here is a sounding from Morehead City. Notice the temperature, moisture plot to the left, dew points are the left, temperatures are on the right. And if you were to bring this up, the actual dry adiabatic lapse rate would go like this. And what we're seeing here is the actual lapse rate isn't nearly quite that much. And if I were to make it saturated, here's a moist adiabatic lapse rate. The air parcel would actually be all the way to the right, all the way up there. So if something can saturate an air parcel down here in the lower levels, some lifting mechanism were to occur, you could actually have that air parcel continue to rise all the way up over 200 millibars and you get a thunderstorm. Now, say we were looking at something different, look out in Ohio, at Wilmington, look how dry it is. So by the same token, you tried to lift it in here. There's no way this parcel is going to get saturated. It's just going to dry out. So it's going to tend to cool. It's going to be unstable. So this is just looking at stability. So I hope you got something out of moisture and stability. And please don't hesitate to ask if you have any questions.